Hi, my name is Ram, and I'd like to briefly go over optimal substructure as well as the greedy choice property. So essentially, you're given problems, and you essentially want to assume that you have the optimal solution to that problem. Of course, you can kind of have solutions, but there are only, a subset of solutions that are optimal. In other words, they solve the problem in, the most optimal manner. So, suppose you have a problem and then you have the optimal solution. Optimal substructure is kind of a property, right, of a solution, right? So basically, optimal substructure states that if you have a solution, right, some larger solution, and that solution is optimal, right? So you actually have some larger optimal solution, um, you can essentially create kind of a new world where you basically strip away a component or element or piece or part of this optimal solution to kind of form a smaller segment, right? And within this smaller segment, right, you've kind of boxed it off and you're saying, okay, well, in this world, for this particular, set of things that I have, this creates kind of its own scenario and it is the optimal solution for the scenario that it has created, right? So what do I mean by that, right? So suppose you're a robber and want to rob a store, God forbid, but suppose that's what you wanted to do. Well, you have what's called a knapsack, right? And so you're looking at certain items that you might want to steal, and certain items are more valuable than other items. And their value is essentially judged by how much you could sell them for later. And your knapsack has a fixed capacity. So basically, you want to optimize, you want to come up with an optimal solution for how you can actually take these items and put them into your knapsack, right? How do you come up with this configuration, right? And your essential job is to maximize the total value of your knapsack, right? So you can imagine that, okay, well, you have the knapsack and you have things in it. Let's say there are five things in it. Ultimately, there was an optimal solution to determine that, five things within this knapsack give you the best value, right, as part of that robbery experience. Um, but then let's suppose, right, you take kind of one item away. If you were to take one item away, you actually have this new knapsack now that has one less item in it. And so you're kind of now in a new world. You suppose that, okay, you know, for that capacity, that is the optimal solution, right? With this kind of new configuration, right? So it's kind of a sub-problem in and of itself, right? So now the value, let's say the value of that bag at the end of the day, before going into the sub-problem realm was $15, right? That's the value of the bag, right? Well, okay, if you strip away an item, let's say now the value is 13. So in this whole world, for these amount of items, and if the value you were trying to reach and the optimal value that you should were trying to reach was $13, well then these amount of items are in fact the optimal amount of items to reach this optimal value, right? 13. So it's kind of your new answer, right? So what you want to essentially think about is take that optimal solution, take off a piece, take off a component, take off an element, and then reframe the world in which this for itself is an optimal solution with these amount of things, absent of that thing I stripped off. And so that's kind of how you create this sub-problem realm, but you're essentially assuming that for that sub-problem, whatever you have after stripping away, that thing off, that item off, that part off, or that element off, that is in a sense the optimal solution for that sub-problem. So that's kind of if so that's essentially what your if a optimal solution has this property that you can fragment, right, and kind of carve out a part and say, okay, well, in and of itself, in its own world, right, this is the most optimal solution. Um, well, then that is an optimal substructure, right? It's a kind of a structure of a problem. It's a property. Another way to think about this is if you had a set of coins and this is kind of this is what's called the making change problem where okay, you have to like make change for 56 cents, in what way should you do that in the most optimal way possible? It should like, basically where optimization in this case means the fewest amount of coins to satisfy this 56 cent amount. How do you do this? So, you can say, okay, well, to make 56 cents, maybe I use these many dimes and these many quarters and these many pennies and these many nickels. That's the optimal solution, right? Um, and then on the other end, you might say, okay, well, let me just remove a nickel, right? Let me just remove one coin. Okay, and let's say removing that one nickel brought you down to 51 cents. Well, okay, then you say, okay, well, if I was actually trying to make 51 cents of change, then these amount of coins that I have would be the optimal solution for making 51 cents, right? So that would be optimal substructure, right? Can I strip something off and now I have a smaller kind of solution set for which that is the most optimal solution. I mean, that's an optimal solution rather for that particular new world I've created now that the parameters have kind of mixed around, right? So this is called optimal substructure. And the idea is that if you want to use dynamic programming or if you want to use a greedy algorithm, again, these are techniques to solve problems. Um, you have to prove that optimal substructure exists. So optimal substructure is in fact, a prerequisite for going either the greedy route or the dynamic programming route. I'll suspend ever so briefly the dynamic programming route for now, and we'll say, okay, well, let's suppose you just, proved optimal substructure. Should I use greedy? Should I not? Right? That's a whole different conversation. The point I want to make here is I've kind of, in a hand wavy sense, said how you identify if an optimal solution has um, optimal substructure, right? But how do you actually do that in practice? Well, what you end up doing is you start with the optimal solution, right? Strip away, one component or item, and then look at the subproblem. And in order to judge whether or not the subproblem is optimal, we do something called a proof by contradiction, right? So a proof by contradiction is you start with an assumption and you trail the implications of that assumption. And if trailing the implications of that assumption negates your assumption, it's a proof by contradiction, so the assumption must be true. So in this particular case, what we end up doing here is, okay, you have an optimal solution. You've stripped away a component to now have a subproblem. And suppose this subproblem um, is optimal. Okay, great. That's what it means to be an optimal solution. But then you actually say, suppose this subproblem is not optimal for its own world, right? And then you say, okay, well, if that's the proof by contradiction part, so you're negating, right? The fact that you're saying if this were a solution with optimal substructure, then this subproblem would be an optimal solution, right? Stripping away that one thing to get this subproblem world, right? Like stripping away a coin or taking an item out of a knapsack. This is now a optimal solution for its own world now that these, parameters have been reconfigured. But because we're doing a proof by contradiction, you actually start by saying, actually, assume this is not the optimal solution. Instead, if it's not an optimal solution, well, then there must be another set of configuration. There must be another set of configuration for which you can optimize the subproblem. And if you can optimize the subproblem, right, then, you know, so this is kind of layer two. There must be another solution, right, that does what the subproblem's optimization was trying to do, but better, right? And if that's the case, great. Then what you end up doing invariably is you end up adding the item back, the part back, the component back that brought you to the subproblem world. And when you add that item back, you actually end up showing and proving that that is better than the global solution. That is better than the global solution, the overall solution, right? And then so basically you're saying, actually, I started by assuming that the overall solution that was optimal. So if I could trail this implication down and come to a subproblem uh, um, that has a better global solution, then the assumption that that was the best thing to begin with is false, right? So that's invariably the step. Start with a problem, take the optimal solution, peel something off, come up with um, a subproblem, and basically you say, okay, well, this is optimal, supposedly, if this problem had optimal substructure. Assume it doesn't have optimal substructure. If it doesn't have optimal substructure, um, well, then there must be another kind of configuration of, a set or whatever that does it better than that subproblem. And if that's the case, great, add that thing back, the thing that brought you to the subproblem to begin with, right? Whether it's a coin or whether it's an item. And then what you'll end up seeing is that optimization is actually better than what you started with and what you had before, the global one, right? The global solution. And if that's true, well, you started by saying there shouldn't be anything better than the global solution, and there is. So then this is a proof by contradiction. There's a contradiction. Everything falls apart, and then, you know, that's it. So that's kind of invariably the mental framing you want for proving if a problem has optimal substructure. You actually do it by proof by contradiction. And then the greedy choice property is, can I, in fact, make a greedy choice, a decision each time that I'm confident in? And then I can't backtrack on that decision. So I make that decision and it's fixed and I make it, and then that's just the way it is. Um, and I can't necessarily backtrack on that decision. Um, and I should be able to make that decision repeatedly to get a globally optimal solution. And so that's kind of, so you have to decide whether a greedy choice property exists. And the way you do that is you say, well, suppose, what would that decision be if I could think about it? What would that greedy decision be to, to make that decision repeatedly to then work up to a globally optimal solution? Well, you know, it might be that, it could be a number of things, right, in any context. But then suppose that that one decision that you're making that should hypothetically lead you to a globally optimal solution is not a good decision. In other words, that decision is not part of some, it's not part of the optimal solution or some optimal solution because there could be many. It's not, it doesn't jibe well, right? It doesn't actually, it's not actually part of that. So then you say, okay, well, then there must be, this is the proof by contradiction yet again. So there must be some other solution, some other decision rather, that you can make repeatedly, right? Or there must be some other decision that works, that's fine. And then you look at that and you say, okay, well, can I swap out, um, uh, can I swap out that greedy decision that I said was optimal before with that new decision that I'm supposing must be there instead if this is not? And if you can swap them out without making the optimality worse, um, and everything is the same, then it's a safe decision to do what I wanted anyways, right? Which was to make that greedy choice. So basically, you're saying decision A is a greedy optimal choice, is a greedy choice that leads to an optimal solution. But suppose it's not, well, then there must be another decision. Great, let's say this decision is optimal. Well, if I take that decision out and put decision A in, and everything's the same, well, then it's a safe choice, right? So if you can prove both of these things, that a problem has optimal substructure and greedy decisions, the greedy choice property is a valid choice, then you can use a greedy algorithm.